this talk is going to be about stars, but actually what it's about is about how astronomy is relevant to you, because as you've just been told, I weigh black holes for a living. That was my job for sort of 20 years, and it gets kind of difficult trying to explain, especially to your mum and dad, why you bother doing that, because they kind of can't see the point. So I got more interested in the idea of why we should be interested in astronomy. What is it that you know, when you become taxpayers, your parents now are spending a lot of money on organisations like the European Space Agency, the UK Space Agency, to put telescopes in space, to put satellites around the Earth, and all sorts of bits of science, but we don't really understand why. And Mr. Barrett mentioned this idea of the European Space Agency. You might have heard the Rosetta mission, the mission that went to a comet, orbited around it, landed on it. That was all about studying water. And last night I was talking to a group about water and why it's important, because it underlies life. Okay, so biology requires chemistry, chemistry requires physics. So what I'm going to talk about now is kind of all three subjects, but as an astronomer, I'm slightly biased, right? As far as I'm concerned, if it wasn't for astronomy, there wouldn't be anything else. There wouldn't be any other subject areas, because it's all down to where the chemistry comes from. So life requires water. Water has to be manufactured, if you like. The elements of water have to be manufactured. Water's only hydrogen and oxygen, nice and simple. But the oxygen wasn't around when the universe began. So the oxygen was made somewhere. And we're going to talk about how you create the chemistry of the universe. So how the chemistry that's in you and everything around you came about. So to do that, we need to cover a few things. We're going to talk a little bit about stars at the beginning, what they are, so a very quick introduction to some of the physics of stars. We're going to look at what's out there in the universe, so not just what we can see around us, but some of the other stuff that is out there as well. Then we'll look at where it all came from, and if you came to the talk that I was supposed to give yesterday but was stuck in Bristol Airport for 3 hours not to come in here, it's all about the Big Bang. Okay? It's about this explosion that began the universe 13.8 billion years ago. But that only created very simple chemistry. It didn't create the complex chemistry that we see today. So we need to know where the chemistry comes from, and then how does it move around? How do you get the chemistry from one place to another? It's all well and good saying, oh, stars make chemistry, but there aren't stars everywhere. So you need to take the chemistry that stars manufacture and shift it around, move it around, so that it eventually forms planets and stars and maybe life. So we're going to cover quite a lot. You all recognise this. I'm sure you can all memorise it and write it down and all that kind of stuff, right? You don't need to worry about the details of this, in a sense. If you become a chemist, unfortunately, you'll have to learn this in even more detail. If you're a physicist, it's really simple. And I'll show you a bit later how I know this entire table as an astronomer. There's a little trick to it. But all these chemicals came from somewhere. All these elements came from somewhere. Okay? You put them together and you make molecules. You make chemistry, effectively. But we need to know where they all came from. Where does the nickel, the gold, the iron, all of those things, where do they actually get produced? The other thing we need to think about is states of matter. Now, you're all familiar with solids and liquids and gases, I'm sure, because you've done those right the way through school. Stars are actually not a gas. We kind of think about stars maybe as being a hot gas. That's often the description that's used. But technically, a star is mostly plasma. It's an ionized gas. It's a gas that's so hot, electrons are being ripped off it. Okay, that's all that means. It's so hot that you're ripping electrons away from the atoms that are in there. Stars are mostly hydrogen. The sun is 75% hydrogen, roughly, 25% helium, and a tiny, tiny fraction of everything else that we see around us all the time. But we're not dealing with solids like the Earth, we're not dealing with liquids like water, we're not dealing with gases like the air that we breathe. We're dealing with extremely high temperature materials, which we would call plasma. Now, recycling is a good thing, right? We're all encouraged to recycle plastic, paper, all these sorts of things. But the universe has been recycling since it was created, and we think that was about 13.8 billion years ago. So this diagram is supposedly showing you a sort of a recycling loop. So I'll explain what's going on. In the middle, you have this dark, fuzzy blob. That's a gas cloud. It's a cloud of mostly hydrogen, but mixed into that is dust. And that dust isn't the sort of dust that we have a nice display of dust on the floor that we arranged for you earlier as you walked in, which is expertly hoovered up. Right? This dust here is powder, it's plaster. Most of the dust in your home is skin cells, hair cells, bits of cats and dogs if you've got them. The dust we're talking about in these giant molecular clouds that float around in the galaxy, and we see them all over the observable universe. We see these giant clouds of gas and dust. It's little grains of metals, metal oxides, iron oxide, titanium oxide, nickel oxides, things like that. So it's not quite the same as the dust in your house. So you have these giant clouds, and they're happily floating around in space, and then every now and then something happens. Another cloud bashes into them, a star moves past them, a star explodes, and a shockwave pushes that cloud a little bit. And that cloud begins to collapse. Gravity is the dominant force in the universe as far as we're concerned in astronomy. Once that cloud begins to collapse, it carries on collapsing. As it collapses, it breaks up into pieces, so it fragments. So you start off with a cloud that might weigh 1,000,000 times the mass of the sun. So there's 1,000,000 times the sun's mass inside that cloud. And it breaks up into clumps. And some of those clumps weigh less than the sun, and some weigh a lot more than the sun, and some weigh roughly the same as the sun. And each of those clumps then individually collapses as well. So you've gone from one giant cloud to lots of little pieces, all collapsing. And all of those little pieces potentially make stars. And there are two basic types of star when we think about the mass, and it's all about mass. It's all about how heavy the stars are, if you like. So on the left-hand loop, we have stars like the sun, okay? Yellow average stars. Our sun is very, very boring in a sense. It's very average. So from that collapsing cloud, a little yellow star will appear. By little, I mean that, I'll give you a sense of scale. Okay? If a pound coin, if that's the size of the Earth, the sun is about that big. You can fit roughly 1,000,000 pounds inside a sphere the size of the sun. Okay? 105 of them roughly will go across. I haven't got 105 pounds in my pocket. But it gives you a sense of the scale. Okay? The sun is a very big object. But compared to some stars, it's quite small. Some stars are much, much bigger than the sun. We'll talk about those towards the end. The sun will live about 10 billion years. Okay, 10 to the 10 years. So the lifetime of the sun, about the length, the time that the sun will live, it's about 10 to the 10 billion years. And the sun is about, well, the sun is, I did this last night, 4.567 times 10 to the 9 years. That's the age of the solar system, age of the sun and the planets, yeah? Easy, 4, 5, 6, 7 billion years. Some geologists are trying to make that an 8, but I'm fighting that because it makes it much more hard to remember. So, our sun and our planets have been around for only a small fraction of the age of the universe. Okay, the universe was around for about 9 billion years before the sun came into existence. And the sun will live for, well, about another 5 billion years, roughly. It's about halfway through its life. The sun is a middle-aged, average, boring star. When it does die, it will puff up and become this big orangey-red thing. Now, this isn't to scale, because if it was, the sun is going to reach a size much, much bigger than it currently is, maybe 100 times its current size. It will swell up, puff up enormously. It will get so big that it will pass the orbit of Mercury, pass the orbit of Venus, and roughly reach the orbit of the Earth. Okay, so when the sun dies, it swells up massively before it actually dies. It becomes what we call a red giant. And it will then start to wobble. It will become very unstable, right? And it gets bigger and smaller, bigger and smaller, bigger and smaller. Eventually, it will just get bigger too many times, and it will just keep expanding. It will puff up one too many times, and it forms a beautiful object called a planetary nebula. We'll have a look at some pictures of it as well. And what it leaves behind, this little white ball that you see at the bottom here, that just sort of fades away into darkness, is an object called a white dwarf. Now, these are very weird objects. They're about the size of the Earth, so 10, 15, 20,000 kilometers across. In this case, the case of the sun, it will probably weigh about half the mass of the sun, which is a big number. That's an awful lot of mass. But that means that the sun's mass, or half of it, is now compacted down into something the size of the Earth. It's incredibly dense. So a white dwarf is a very, very dense object, a very strange object. And that's basically what will happen to the sun. In 5 billion years' time, it will puff up, it will start to wobble, it will puff up one too many times, throw out gas, so you can see this material spreading out in the planetary nebula, it's puffing outwards. That gas then gets recycled into the gas and dust clouds. So when the sun dies, it will throw back some of its chemistry back into the gas and dust clouds, and eventually that material will then form another generation of stars. And the white dwarf will just cool down, will just do nothing for a long, long, long time, and fade away, get colder and colder. So the sun and stars like it are not very exciting. They don't make much chemistry, as we'll see. Right-hand loop is the interesting one, because that's where most of the fun chemistry comes from, most of the interesting stuff in the universe. This is clumps of matter, clumps of gas that fragment, break down, that are maybe 10 times the mass of the sun or more. Okay, so you're looking at a star which is at least 10 times the mass of the sun. And they then form these big blue stars, okay, blue giants, blue supergiants as well. So these blue stars will live very short lives. I said the sun is going to live about 10 billion years. So you might think, well, a star that's 10 times the mass of the sun, it has 10 times more fuel than the sun, maybe it will live 10 times longer. It actually lives 1,000 times less. It kind of works the other way around. So stars like the sun are kind of, I don't know, Toyota Yaris-y, hybrid-y type car, right? They're the sort of car that just can do 100 miles to the gallon type thing. Yeah, very, very good fuel efficiency. Whereas the massive stars are your Formula One racing cars. They do, a couple of 100 meters per litre. Incredibly fuel inefficient. The more massive the star, the shorter its life. So stars that are, say, 100 times the mass of the sun. So we talk about 100. The symbol for the sun is a circle with a dot in it. Their lifetimes will be about 1 million years, something like that, at most. So a little star like the sun lives a long, long time, 10 billion years. A massive star lives much, much less life, has a much shorter lifetime. But it lives a much more spectacular life. When it puffs up, after about 1 million years, it becomes not a red giant, the size of the Earth's orbit, but a red supergiant. That could put it somewhere out past the orbit of Saturn. Imagine a star that's so big, if you put it in our solar system, it would fill all the space from the sun out to Saturn's orbit. And we see stars that size, huge stars. Again, they get cooler, so they go from being blue hot to red hot. I'll talk about that in a minute. But they don't die in the same gentle sort of puff up, shrink, expand type way that the sun will. They blow themselves up. They explode in what we call a supernova. And we now have things called hypernova. We've gone beyond a supernova, so it's a if we have something else, it'll be an ultra super hypernova. We kind of come running out of superlatives, right? But these stars blow up in these supernova explosions, and they leave behind really weird stuff. So white dwarfs are odd, half the mass of the sun in the volume of the Earth. They're very, very dense. But the other end objects, the top one there with the lines going, that's a neutron star. That's maybe 10 kilometers in diameter, and it can weigh up to maybe twice the mass of the sun. So take the mass of the sun, double it, and then crush it down until it's the size of Aberdeen, roughly, something like that. Yeah, it's an incredibly dense object. And again, if you go into university, you'll get into the physics of how an object can be that dense and still survive, and it all gets very quantum physics-y. And the other object it could become, if it gets really crushed down, is everyone's favourite black hole. Okay, you punch a hole in space and time, and things get very, very weird. So all of these processes, this explosion of a star, throws material back out into the universe. So a planetary nebula is a gentle death. The material is moving at about 400 kilometers per second. It's about 200 times faster than a bullet. But that's gentle for the universe. When a star goes supernova and it blows itself to pieces, it throws its matter back out into the universe at something like 4,000 kilometers per second. 1,000 times faster than a bullet. And we can actually see stars which have died where we have the explosion, a cloud of exploding material, which is moving out. We can track its motion over time and see it expanding. And of course, that expanding material then gets recycled. It goes back into the gas cloud. It might even trigger a gas cloud to collapse. So one star dying could, the explosion, if you like, it hit the gas cloud and trigger thousands or millions of stars to be born. So it's a very, very efficient recycling process in that sense. When one star dies, it throws its chemistry back out into the universe, and it maybe triggers a new generation of starbirth. When we look at the sun today, we can calculate that looking at the chemistry that's in us and everything around us, there have been at least 2 generations of stars that went around this right-hand loop, the massive stars, 10 times the sun's mass or more, before the sun was born. Okay? And we know there's a lot of time. That's how old the solar system is. And the universe is 13.8. Awful lot of time before the solar system came into existence. In that time, at least 2 generations of stars have been born, lived, and died, and blown themselves up, and thrown their chemistry back out. We know that because of the chemistry that we see. What's happening is those gas clouds start off as pretty much hydrogen, and they give birth to hydrogen stars. And then those stars make chemistry, so when they die, they throw out this new chemistry, the helium, the lithium, the iron, the carbon, all these other chemicals. They get thrown out into the universe, so the next generation of stars aren't just hydrogen. The hydrogen plus the stuff that the first generation created. That next generation of stars lives and dies and blows up and processes material. And then the third generation of stars, like the sun, pick up 2 lots of recycling that happened before them. So the chemistry is very different. So we think the original stars, the ones that were born right after the Big Bang, were almost 100% hydrogen. They were almost pure hydrogen stars. They were enormous. They could have been thousands of times the mass of the sun. Nowadays, stars like the sun are something like, I'd say, 75% hydrogen. So the percentage of hydrogen is going down, and the percentage of other chemicals is going up. Other elements is going up. Yeah. Right. Key lesson. We're going to learn a bit about the physics of light, if you like, because you'll come across. You haven't done this yet, but just in simple terms, stars are not like taps. Okay, I mentioned this to somebody yesterday. It sounds like a statement of the extremely obvious, but if you think about taps, a blue tap is cold and a red tap is hot. Stars are the other way around. Okay? A blue star is a hot star. A blue star is 30, 40, 50,000 Kelvin, very, very high surface temperature. A cold star Well, cold is a relative thing, right? To us, cold is kind of 0 degrees Celsius, something like that. You feel cold then. But for a star, cold would be 2,500 Kelvin. Yeah? Much, much higher temperatures than we're used to, but for a star, 2,500 is relatively cold. So stars cover a range from, say, 40 or 50,000 Kelvin down to about 2,500 Kelvin at the opposite end. And the temperature determines the colour. And that's the important bit of physics that you'll come across next year, but we'll talk a little bit about in a minute. Another thing we need to know about stars is how bright they are, how shiny, if you like, how much light they give out. Yeah? This room is being illuminated by lights in the ceiling. Those lights give out a certain amount of light, and obviously if they were bigger, they could potentially give out more light. So when we think about stars, we're thinking about we call it luminosity, right? How much light they actually give out every second, hour, minute, whatever it is. There are two things we need to think about. How big is the star? And in effect, it's its area that's important, right? The surface area that the light is shining out of. And then how hot is the star? So how hot is every square meter of that star? And then how many square meters do you actually have across the surface of the star? And to make things simple, because in physics we want to make things simple, I don't want to go out to the sun and measure exactly how hot it is, because that would be a little bit dangerous. I want to make some assumptions, but I want them to be reasonably good assumptions. So we assume stars are spherical. We assume they're all perfect spheres. Some of them are not. Some of them are horribly kind of M&M shaped. They're kind of flattened and squished and bulging at the equator. So some stars are very, very not spherical. But as an approximation, let's assume a star is a sphere, because then we can calculate the surface area of a sphere. And we assume there's something like called a black body, a perfect emitter and absorber of radiation. Now again, you'll come on to this, but for now we just need to know that there's an interesting bit of physics that relates to temperature and wavelength of light that are emitted. Stars are not either of those things, right? But it's a good first starting point. So you will come across this thing about black bodies and a thing called Wien's law. The curves on the left are the important bit, okay? So you have wavelength increasing to the right. So on the bottom, on the x-axis here, you're going from gamma rays and x-rays on the left through to radio waves and things on the right-hand side, yeah? And at the y-axis, you have intensity, brightness. How bright is the object? And you'll see that there are 1, 2, 3, 4 curves marked there. So 3 curves marked there. 3,000 Kelvin is the lower one. 6,000 Kelvin is the middle one, and 12,000 Kelvin is the high one up on the top. And you've got the optical spectrum, a little bit of light that we can see with our eyes marked orange. There's an equation, lambda max, so the maximum wavelength, the peak wavelength, where the top of that curve is equal to a constant divided by the temperature. So that tells you there's a relationship between the wavelength that the curve peaks at and the temperature. The higher the temperature, the 12,000 curve, the shorter, the lower the value of the wavelength, right? The inverse. Temperature goes up, you go from 3 to 6 to 12,000. The wavelength at the peak of that curve goes down. The light gets bluer, effectively. Yeah? Does that make sense? So hot things look blue. This is what I was saying about not being like taps. Look at the lower curve, 3,000 Kelvin curve. This little bump at the bottom. The peak of that curve is at around 1,000 nanometers. That is basically the infrared part of the spectrum. We couldn't see most of the light from that star because it would be beyond the range that our eyes can see. Dogs can see it. They can see into the infrared far more than humans can. The star in the middle, the 6,000 Kelvin, well, its peak is in the kind of bluey-green part of the spectrum. That's about where the sun is. Now, the sun looks yellow, but that's because the atmosphere filters light and does things to it on its way. 12,000 Kelvin curve peaks beyond the violet part of the spectrum. It's in the ultraviolet. Yeah? It's too blue for our eyes to see. So this is why hot stars look blue and cool stars look red, because of this relationship, this idea of black bodies and Wien's law. Again, you'll cover this in more detail in the next year or so. Just to show you that the black line here is one of these black body curves, and the white line is the actual light coming off a real star. And you'll see that it doesn't match, right? There are all sorts of jaggedy bits in that white line that aren't in that lovely, smooth, theoretical curve. But it's pretty close, right? It's a reasonable approximation for what we're trying to do. But it's not spot on. But then in astronomy, most things are fairly approximate. So if we want to work out how bright the star is, we need to know its temperature. Well, we can do that by looking at its colour. If it's blue, it's hot. If it's red, it's cold. If it's yellow, it's somewhere in the middle. We can make a plot, a graph, of how bright the star is at different wavelengths, draw a curve through it. The peak of that curve will tell us the temperature. So we can quite easily measure the temperature of a star by just looking at its colour. It's a bit more complex than that, but essentially that's what it is. A star like the sun is yellow, it's about 6,000 Kelvin. A really hot star is 10, 12, 15,000 Kelvin. cold star is a couple of thousand Kelvin. Yeah? So we can measure temperature just by looking at the colour of the star. So the luminosity, we said, is equal to two things. It's effectively a function of the temperature, but we've just figured out how to do that. But you'll see the temperature term on the right-hand side is T to the 4. So it's the temperature multiplied by itself, by itself, by itself, T to the power 4. And a constant called the Stefan-Boltzmann constant. It's just a number you can look up. And the left-hand term, the one I put in brackets, is just the surface area of a sphere. So we've assumed the star is spherical. We said, okay, let's try and work out how hot it is. So we know its surface temperature. We know the area of the thing. We multiply those two together, that gives us the luminosity. So that's how bright the star actually is, right? Because the sun is really close to us. So when we measure the temperature, when we measure the sun, it's the closest star to us, and we can do lots of good measurements on it. But other stars are really far away. We can't go to them and make really detailed measurements. It's very hard just to go to the sun, never mind to go to stars that are hundreds of light years away. When we put the numbers in, so we put in the values for the sun, its radius and its temperature, all that kind of stuff, we can calculate the luminosity of the sun as if it was a light bulb. And the sun is a lot of light bulbs, 3.84 times 10 to the 26 watts. So every second, the sun is beaming out 3.84 times 10 to the 26 joules. Very energetic object. And it will do that for 10 to the 10 years. And there's only one way you can keep a star burning at that brightness for that length of time, and that's nuclear fusion. That's what we're going to look at. The other thing is, stars all appear to be little white dots in the sky, right? The sky is clear today, so if it's clear tonight, look up, you'll see lots of stars. You'll be able to say, okay, if a star looks red, you'll know that that star is probably relatively cold. There are some stars you can actually see that do look red. If you've got a pair of binoculars or a small telescope, it's easier. But your eye can actually see some stars that look a little bit redder than others. But all the others look like white dots because your eye's not very good at picking up. The next problem we have is that stars are at different distances from us. So the sun is a fairly average star, but it's really close to us. So it looks very, very bright. Imagine you had a really, really bright star that was really, really far away. It would look very dim. But you need to know not just how luminous, how bright the star is, but also how far away it is. That's a function of distance. The further away a star is, the fainter it will appear. And the way that light appears to get dimmer is what we call an inverse square law, 1 over r squared. What that means is if I double the distance, if I make the distance 2 instead of 1, 1 over r squared, I've doubled the distance, the star appears to be a quarter of the brightness. Yeah? If I put it 10 times further away, it's going to be 100th of the brightness. It's a nice simple relationship. As the star gets further away, it looks fainter. So if we know exactly how bright a star is, and we know how bright a star appears, we can work out how far away it is. But we can do some interesting things. Just by taking pictures of stars, we can estimate their temperature, if we assume they're spherical black bodies. And if we then work out their temperature, their luminosity, all those other things, we can estimate how far away they are by taking pictures of them, colour pictures. Okay, so where did this all come from? Well, we start off with the Big Bang Theory. That's our model for the universe, our current model. There are others, but this is the best model that we have. And according to that theory, the universe began about 13.8 billion years ago. It created hydrogen and a little bit of helium, and that was basically it. And then stars have done the rest. So this room is not full of just hydrogen, right? Nitrogen is 80% of the air that we're breathing. There's a lot of other chemistry in this room. Well, that wasn't made in the Big Bang. It had to come from somewhere else. So as an astronomer, I have quite a simplistic view of chemistry. But it's an easy one because it allows me to reproduce the entire periodic table of elements, okay? So probably just enough space over here. So you saw the periodic table earlier, right? You've all remembered it and revised it and everything. So we've got hydrogen, okay, in the top left. We've then got helium, and that's what was made in the Big Bang, hydrogen and helium. Now we have all this other stuff. As far as I'm concerned as an astronomer, okay, if I start to fill this in, I've got hydrogen, helium, and then everything else, metal. I don't care what it is. All I care about is how much hydrogen there was, because that's going down, and how much of everything else there is now, because that's going up, because the hydrogen is being used to make all this other stuff. To an astronomer, chemistry is really simple. If you become a chemist, you have to fill that in. It gets really complex, so don't become chemists. It's really complex. An astronomer, this is all we need to know. Hydrogen, helium, metal. Everything else, even if it's oxygen, we call it a metal. seems kind of odd, but from our point of view, it doesn't matter what it is. It's not hydrogen and it's not helium, it's something else. So this is our version of the periodic table after the Big Bang. This weird explosion that created the universe 13.8 billion years ago, made the top two elements in the table. Right? Those are our building blocks. And from those we can make everything else by adding them together, by crushing them together. So immediately after the Big Bang, there wasn't a lot you could make stars out of apart from hydrogen. So your stars were hydrogen stars, massive hydrogen, pure hydrogen pretty much. Those stars made chemistry. We'll show how that happens in a bit. So they took hydrogen and crushed it together to make helium. They took helium, crushed it to make carbon, nitrogen, oxygen, took those elements, crushed them to make the chemistry all the way up to iron. When you get to iron, you have a problem. Because in the interior of a star, if you're crushing elements together and you're releasing energy, that keeps your star up. It keeps it inflated against gravity, which is trying to crush it down. Once you get to iron, you have a problem, because as you crush iron and you try to add other elements to iron to make new things, gold and silver and lead and that kind of stuff, suddenly you find that it doesn't give energy out, it effectively pulls energy in. It's kind of like an exothermic reaction against an endothermic reaction. Yeah? Exothermic gives energy out, endothermic pulls it in. It's the same sort of principle. So these stars, which up until that point, until the creation of iron, have been booming energy outwards and holding off gravity, suddenly they don't hold off gravity anymore. And it all starts to go horribly wrong for the star at that point. So stars make all the chemistry up to iron. Okay, so any element you see on there that goes up to iron can be manufactured inside a normal star, a massive star, but inside a star. The sun will only create chemistry up to about carbon, maybe nitrogen, something like that. It won't be able to, it doesn't go as far through the table as the really massive stars. The biggest stars, the most massive stars, will go all the way up to the top end. Hello?
Will you just come in and sit down?
Why not? Yeah, why not?
Is this?
No, we came I think last night. Like.
Oh, right. Yeah, yeah, we're talking about stars today, not meteorites, but yeah, grab a seat. We've missed a little bit, but basically stars make the universe, that's the bottom line, right? So you've got chemicals being manufactured inside stars all the way up to iron. And then once you go beyond iron, you need another way of making chemistry, and you do that by blowing the star up. So the rest of that periodic table is made in a supernova. It's made in the explosion at the end of a star's life. When the star blows up, it can create all this chemistry, because suddenly it's not a nice controlled reaction where the star is kind of crushing all these elements together and making energy and making the chemistry. It's an explosion. It's a chaotic event which releases huge amounts of energy. So the universe is made of stuff. And if you were in the talk yesterday, you've had a little bit about what the universe is made of. And it's made of the stuff that we can see, which is what we've just talked about, right? The chemistry of the universe, hydrogen, helium, and all the other stuff that we just call metal, because we don't care what it is. And that's what we look at. We see clouds of gas. We see stars that are made of hydrogen, helium, and so on. We see planets that have iron cores and oxygen atmospheres, that kind of thing. Okay, so what we see around us is chemistry, really. That's the stuff that we see. But the problem is there's an awful lot of universe that isn't visible. We see a lot of stars. Stars are plasma. They're ionized gases. Gases that are so hot, electrons are being ripped off them. Everything else we see is solids, liquids, and gases. But most of the universe is gas clouds that we see. The problem is, most of the mass of the universe, if we weigh the universe, and that's a whole set of lectures I'm not going to give you, but we can weigh things, right? We can look at how heavy they are. We have a problem then, because we realize that 96% of the mass of the universe is invisible to us. And we call it dark energy and dark matter. And we can even work out what percentages. So 73% of the mass of the universe is what we call dark energy, and 23% roughly is what we call dark matter. Now, dark is a bad name in a sense, because it makes it sound like it's big black clouds of something. I would think the better name for this stuff is transparent. Right? This room could be full of dark matter. We can't see it. It doesn't react to light. We can't X-ray it. We can't look at it in infrared or radio or optical. We just don't see it at all. But it's here. It has mass. The problem, the stuff we can see is that little sliver in the corner, the 5% or so. 4% of that is hydrogen, or most of that is hydrogen and helium, and a little 0.5% is stars. So most of the mass of the universe is totally invisible to us. The only analogy I can kind of give you really is to say, okay, well, this room is full of air, right? We can't see the air, can we? We know it's here, because we'll be dead otherwise, right? So you breathe it in so you know it's there. The only way you can see that air is present, in a sense, apart from there being lots of dead people in the vacuum, is if you see a windy day, you see trees blowing. You look out the window, you see the trees moving. And the fact that the trees are moving tells you there must be something out there that's moving around, that's making the leaves and the branches move, right? So we can't see dark matter, but we can see the effect it has on other things, like stars and galaxies. So we know that most of the universe is invisible, not because we can see that stuff, it's invisible, but because of what it does to other things, what it does to stars and galaxies in particular, right? So without going into the whole what's going on out there in the universe, because we don't know what dark energy and dark matter are. And that's kind of embarrassing. So after thousands of years of studying the universe, we vaguely understand what a few percent of the universe is made of. So the more we look, the more we realize we don't understand the universe. There's some big discoveries to be made out there. These are Nobel Prize winning things. Whoever discovers what this stuff is definitely on for a Nobel Prize in these areas. Anyway, so that's the embarrassing bit, right? So let's go back and look at the chemistry. Let's look at the bits that we think we vaguely understand and how this all comes together. So this is a nursery. This is a star-birth region. Very pretty, colourful. What we're looking at is a huge gas cloud, but effectively you've got to imagine this is a two-dimensional picture, right? A flat image. And it looks very pretty, lots of colours and everything in there, lots of stars and other things, structures. What you're looking at is a three-dimensional universe, right? You're looking into something, it has depth. You've got to imagine almost this is a cave. You're looking into a cave in a cloud of gas. And the stars, those lovely pinky stars you can see in the middle, they are blowing winds off their surfaces. Stars emit material, not just light, they emit material as well. And that material blows away the gas clouds around them. So once a star is born, it starts to sweep away all the dust and gas that was around it. And if there are lots of stars, like there are in this region, all of them start to sweep away the material, and you start to blow a hole, a cavity inside the gas cloud. And that makes it harder for more stars to be born. So once the first generation of stars is born, they kind of stop the next generation being born because they remove the raw material. Again, the analogy is like, imagine you've got a load of bricks and you're trying to build a house. And every day, you build a bit of your house and you go to sleep, and in the night your neighbours come along and they nick some of the bricks that are left. And when you come back in the morning, there are less bricks there for you to carry on building your house. The longer you take to build your house, the smaller your house is going to be, because every night the neighbours are nicking a few of them, yeah? So in the same way, you start off with big stars, they start to blow away, they start to remove that raw material. So later stars can't be very big because most of the gas and dust has been removed, been blown away by the big bully stars. When we look at the chemistry of these clouds, we look at the chemistry of what's inside these big columns, these fingers, and that central feature there, I'll show you on this one, this column here, these are called the pillars of creation. This is an amazing Hubble image and showing you this region. This is about 2 light years long. So if I took a laser beam and shone it from here, it would take 2 years to reach the other end. And light is very, very fast. Okay, so that's an enormous amount of material in that one little finger. And there's a huge amount of material in this region. So lots of potential for lots and lots of stars. And the chemistry is quite complicated. There are some simple things. Molecular hydrogen, salt, sodium chloride, oxygen, iron oxide, and carbon monoxide. So it's very, very basic chemistry. But we've also found quite complex chemistry. We find things like formaldehyde, acetic acid, amino acid, toluene, or whatever, right? Stuff with lots of hydrogen, carbon, nitrogen, oxygen. Those 4 elements, we call them, okay, I know I said metals, we don't know it, but just to keep the biologists happy, right? Chon. So as an astronomer, we do allow oxygen and carbon to be considered a little bit interesting as well, and nitrogen, because those are the elements for life, for organic chemistry and all that kind of stuff, right? I'm not a biologist, but as far as I understand it, that's what you need for life, right? And you'll see that in these clouds, there are lots of different molecules that have these components in them. So the chemistry for life is in these really weird, freaky-looking clouds. And these clouds have enough material in them for thousands, maybe millions of stars. And each of those stars could have planets, and each of those planets could potentially have life. So when you start to think about life in the universe, the numbers start to get really, really big. But we've never found it anywhere other than Earth. It's the only place. Zoom in on those columns, on those pillars. The left-hand one, imagine, is about 2 light years long. The little stumpy one on the end is only a light year long, something like that. This is what they look like in the optical. So our telescopes can't see into those thick gas clouds. You can see a couple of stars on the outside, right? And they're blowing winds which are moving all the material away and just leaving these dense columns in the way. But if we look in the infrared, we go to slightly longer wavelengths, the sort of wavelengths that we use our remote controls and things to turn TV channels. The columns kind of disappear, and now you see inside them. Because infrared light can see into these thick clouds of gas and dust. And suddenly, you notice, for example, where there was one bright star next to that kind of little sticky up finger thing, if we go to the infrared, suddenly there's a bright star right next to you. So you just lower to the, down to the left of it, there's a really bright star, I'm not tall enough to do this, right here. Right there. And there are lots of other stars inside that cloud. We just can't see them in the optical. So we have to use infrared telescopes and radio telescopes to actually look inside. And suddenly, there are hundreds of new baby stars embedded in those clouds. So we can actually see stars in the process of being born. So this helps us to develop our models and our theories. This is one of my favourite Hubble peaks. This is a thing called Magic Mountain. And what you've got to imagine is this is one of these kind of gas clouds, right, with all the raw materials. And there are lots of stars embedded inside this that we can't see. To the top left, there's a big bright star. Hello. And the light and the wind from that star are kind of blowing down across this region. And you can kind of see, almost like the bow wave on a boat, you can see trails of material streaming away, right? So you look up here, for example, there's a star here being born, and material is being blown away from it by the light and the wind from the big bright star top left. And this one, so you can see this almost like you can see a trail, yeah? You get that real sense of material streaming away. So we watch this happening, we have images of this. And over time, there'll be more and more stars born, and therefore less and less gas and dust. And those stars will shine, and they'll blow that big cave inside that giant cloud. Yeah? So here's a picture where you've got thousands of baby stars. Babies are millions of years old in this sense, right? So it's, again, a slightly relative thing. And around it is the remains of the gas cloud from which they were born, from their nursery, effectively. So we're seeing starbirth taking place. Can you see the star here, which is clearly not the same colour as the others? If it's an orangish coloured star, it's a colder star, a cooler star. This was once the most massive star in this group of stars, in this cluster of stars. It has now reached the end of its life. It's puffed up. Remember I said these stars inflate to enormous sizes. As they inflate, they cool down. So instead of being blue, hot like these ones, it's now orangey red hot. It's expanded to become a supergiant, a red supergiant. So just from looking at this picture, I can tell you that even though these stars are probably all the same age, they're all born at roughly the same time, that one is the most massive, because it's the one which is now beginning to die. And the more massive a star is, the shorter its life is. Yeah? So that's, an image can tell us something useful like that. And as time goes on, the cavity gets bigger, the stars start to drift apart from each other, and you get spectacular pictures like this. This is a beautiful image for a lot of reasons. So you've got the gas cloud, you've got some of these pillars, these columns that we saw in the earlier Pillars of Creation image, you've got your beautiful bright stars in the middle, but you can also see these little fuzzy blobs here, and this one in particular, these are galaxies. So a galaxy is like a city of stars. 200 billion stars in the Milky Way, for example. Ours is just one of those. So here we're seeing stuff relatively close to us. This is within a few hundred light years of the Earth. This galaxy and these little fuzzy blobs that you see around it, and up here, these will be millions or tens of millions of light years away. So we're seeing an enormous distance into space. We're looking at something close to us, we just happen to be seeing something far away as well. It's like me taking if I was taking a picture of this computer, I'd accidentally take a picture of the whole bunch of you in the background as well. Yeah? I'm not interested in you lot, I just want to look at my shiny computer. But you happen to be in the picture accidentally. It's the same thing here. You see these beautiful spiral structures and fuzzy blobs and edge-on things, all sorts of structure, yeah? Just captured in these images where we're looking at something actually quite close to us. Now, it turns out that if we plot things, which is what scientists do, we like to make plots, kind of running out of board rubber space or anything like that, but this diagram is one of the most important in astronomy. It's quite a simple diagram in a sense. We have temperature on the bottom, hot on the left, which is 30,000 degrees, cool on the right, 3,000 degrees, okay? And we have colour. Blue stars are hot, yellow stars are average, red stars are cold. So that's what we're thinking, right? Temperature, but it increases this way. And then going up here, we have luminosity, brightness, that we looked at earlier, how big the star is and how much light there is shining out of every square meter. So, anything in the top left corner is going to be hot and bright. Yeah? Anything in the bottom right corner is going to be cold, relatively speaking, 3,000 degrees, and dim. And what you notice is when we plot where the stars are, we look at the stars, we measure how bright they are and how hot they are, they don't just fall all over the diagram, they form a big line across the middle. We call them 90% of stars spend 90% of their lives somewhere on that line. You can see where the sun is, it's kind of towards the lower end, but it's a fairly boring one. It's here, right? It's a yellow star. These are the massive blue stars that live 1 million years, and these are the really, really dim red stars that just live forever, effectively, live for trillions. But stars like the sun live 10 billion years, big massive stars live 1 million years. 10 times less, they have really, really short lives. So, if we we plot where the stars are, we start to get a sense of the range of values. So up here, this is plotting stars 60 times the mass of the Sun, 30 times, 10 times, all the way down to the mass of the Sun here. And you'll see it gives a lifetime. So the Sun, 10 to the 10, 10 billion years. As you go down, then the lifetime increases. That's 100 billion years. 1,000 billion, a trillion years will be down here. So enormous amounts of time. A star like the Sun will live 10 billion years. It's halfway through its life now, right? 4.567 billion years. Go up the line here, the lifetimes get shorter. 1 billion years, 100 million years, 10 million years, and then 1 million years of it. So the more massive a star, the brighter the star, the shorter its life. So where your star is on this diagram determines almost everything about it. How it lives, how it dies. At the top, they blow up as a supernova. In the middle, they just puff up very gently, and at the bottom, they just basically go out. They just get dimmer and dimmer. We won't worry too much about the other regions on that diagram, but they're helpful. They help us understand where stars move. And this is just a little plot. Chuck in. These are masses of stars from half the mass of the Sun, to 25 times the mass of the Sun. How bright they are. So this is the luminosity. The Sun is 1. So a star that's 25 times the mass of the Sun is 80,000 times brighter than the Sun. Okay, so that gives you a sense of how the brightness starts to increase as well. And its lifetime is 7 million years. So 25 times the mass of the Sun, 7 million year lifetime. 100 times, something like that, is going to be way down on that again. So, big stars have short lives, high temperatures, high brightnesses, high luminosities, and they're the ones that are going to make the interesting chemistry. So that's what we'll finish off by looking at. Okay, so, we have a problem. Gravity tries to crush everything. Gravity is trying to pull all of you down to the center of the Earth, right? That's what gravity does. And with stars, you have this enormous ball of plasma, effectively a very hot gas, that gravity is trying to crush down to a central point. So in order to keep that star up and shining and inflated, you need a force that's equal and opposite to keep fighting against gravity. So gravity, imagine, is the black arrows pulling in, and opposite, each one of those arrows is an equal and opposite arrow in red, which is essentially heat. It's the thermal pressure. It's the high temperatures inside the star moving the gas around, fighting off gravity, like blowing up a balloon. Right? You have to keep the balloon inflated to stop it fuzzing down and collapsing. You have to keep the star inflated, otherwise it collapses. So you have to have energy inside the star to keep the star up, to keep the star inflated, if you like. And that energy comes from this equation. This is the one equation, right, that everyone knows, I think they know. E equals mc squared. Energy equals mass times the speed of light squared. What that tells you is if you can convert mass into energy, you get a lot of energy out. Because you're multiplying the mass by the speed of light, which is big, squared, right, the speed of light by itself. What the Sun does is it takes 600 million tons of hydrogen, shoves it into its nuclear reactor, into the core at the center of the star, and out of that pops 596 million tons of helium. And you'll see the scales are imbalanced because you've lost 4 million tons, right? So the M in here is 4 million tons. You multiply 4 million tons of mass by c squared, that's an enormous amount of energy. And that is every second. And every second, the Sun loses 4 million tons. And it's going to do that 10 to the 10 years. That's an incredible amount of weight loss. That's a crash diet like you've never seen, right? 4 million tons per second. So the Sun is burning fuel at an amazing rate. What it's doing is it's taking hydrogen, the simplest element, and making helium, the next simplest element. That's all it's doing. All it's doing. Right? But by doing that, it releases enough energy to keep the Sun inflated. This goes to the chemist. This is the chemistry of what's happening. We call this the PP1 chain. There's a PP2, PP3. Start off with what we call these things hydrogen nuclei. What's hydrogen made of? What's simple hydrogen made of? What bits are in hydrogen? Yeah, proton, anything else? What goes around the proton in hydrogen? Electron. Right? You've got two things, proton and electron. This is described as being a hydrogen nucleus. It's a proton, basically, but it sounds better to call it a hydrogen nucleus. So you start off with 4 of them. 1, 2, 3, 4. You take 2, you crush them together. It releases a little bit of energy. It releases a thing called a positron, and in this case, a thing called a neutrino. You hold your finger up, billions of neutrinos go through your fingertip every second. The universe is full of neutrinos. They go through everything. They go through the Earth, they go through stars. They don't see matter. They seem to just go through it in a ghostly way. Another hydrogen nucleus, another proton comes in, so you crack these two things together, you've made a strange type of hydrogen. You then crash another one in, you you've made the beginnings of a helium nucleus. You do this reaction twice, you cram that together, 2 of the hydrogen nuclei pop out. So you start with 1, 2, 3, 4, 5, 6. The 2 come out, so you've used 4 of them. And at the end of the day, what you end up with is a helium nucleus. So 4 hydrogen nuclei go in, 1 helium nucleus comes out. This has slightly less mass than these 4 protons added together. That mass is where the mass loss comes. This reaction occurs something like 10 to the 45 times per second inside the Sun. You add all those reactions up, it's about 4 million tons of mass loss per second. E equals mc squared. It's not quite as simple as that, but basically that equation works. And you get a huge amount of energy out, enough energy to keep the Sun burning. There's enough mass inside the centre of the Sun to do that for 10 billion years. 1 million tons of mass loss per second, the Sun can burn for 10 billion years, 10,000 million years. It's an enormously powerful reaction. But there'll come a point where you've run out of hydrogen, right? You're turning hydrogen into helium. So it's like shoveling coal into a fire. You're burning the coal. And at the end of the day, you've got no coal left. You've got a load of ash in your fireplace, and that's all. So the Sun will have the same problem. It's hydrogen in the core, where it's hot enough and dense enough for this to take place. It will become helium, and then eventually it will run out. And a star like the Sun, that left-hand loop you saw right at the beginning, that's kind of what happens. It shovels all the coal into the fire, turns it into ash, and that's kind of the end of it. It doesn't really do very much more. It's made helium. It might be able to burn some of the helium and make carbon and some other elements, but not very much. So it makes really simple chemistry. It's the massive stars that can do the interesting stuff. As the Sun dies, it will expand and puff up. Okay, so the little dot in the bottom left is the Sun as it is today. The big red circle here, this is the friendly giant, so probably not that friendly. This is how big the Sun will be just before it dies. At the end of its life, it will be massive. It will come out to about the size of the Earth's orbit. The Earth would have drifted away. The Earth is drifting away from the Sun now. Right? The Sun is losing 4 million tons per second. Its gravitational pull on the Earth is therefore getting weaker, so the Earth's orbit and all the planets are slowly drifting outwards. So the solar system is expanding over time. It's gradually shifting away. And this is how the Sun will end up when it dies. It will look like one of these beautiful planetary nebulae. Right? These are objects that we see. Again, remember, these are 3-dimensional. Stuff is coming towards us, away from us. We kind of only see the 2-dimensional. Imagine squashing that against the screen. The centre is the white dwarf. That's the old nuclear reactor from the start. And around it, these beautiful colours are telling us something about the chemistry. It might have made neon, it might have made carbon, oxygen, just some basic, simple chemistry in there. How the Sun will die, it will spend most of its life on that part of the diagram. It will then blob up here, become a red giant, wobble back and forth, then become a planetary nebula, and then what gets left behind is that white dwarf, which just gets colder and colder and colder over time. So the Sun will have quite a boring death. So this is where the real chemistry comes from, the massive stars, 10 times the mass of the Sun, maybe up to 200 or 300 times. They lead short lives, relatively speaking, 1 million years, but they blow themselves up. Before they blow themselves up, they make the much more interesting chemistry, the bottom end of this. So we call this process nucleosynthesis, making nuclei, making atoms, effectively, making chemistry. The nuclear reactor is the core, the central region. It's hot and dense, and that's where all the energy is being produced. At some point, you run out. Your hydrogen is now all being burned up. Your coal has all been turned into ash. You've run out, right? You now no longer have that outward force that's holding off gravity. So suddenly, the core begins to collapse because gravity takes over and the whole thing starts to fall in on itself. As the core collapses, the temperature and density start to go up. It now gets hotter in the core, and it may come to a point where that ash that you have left over, in this case helium, becomes a new fuel supply. Like I said, it's like shoveling coal into a fire, burning the coal and having ash, and then saying, actually, do you know what? I can burn the ash. I can make ash 2. And then when all the ash 2 is used up, I can make ash 3, and I can keep on going. I can keep on burning these chemicals. Because that loop goes round and round and round, and you make all the chemicals up to iron. And when you get to iron, you have this problem in that iron doesn't give energy out, it sucks energy in if you try and do this same trick with it. And at that point, the star is doomed. There's nothing else it can do now. It can't burn iron to make more fuel. You've reached a point where you now really have run out of fuel. And if it runs out of fuel, you've got to the point where you've made all of these chemicals up to iron, then the star dies, then the star blows up. And this is a picture of a star blowing up. This is a beautiful image from the Faulkes Telescope in Hawaii. Here's a spiral galaxy, and that star wasn't there a couple of days before we took this picture. Well, the star was there, but we couldn't see it. It was way too faint. It blew up in the course of a few days. And that image is showing us the supernova. That little blob there is the exploding star. That happened about 35 million years ago. It took the light that long to get from this galaxy to us. So it happened a long, long time ago, but we saw it in June and July 2011. A star that will go supernova at some point is Betelgeuse, Betelgeuse, in the shoulder of Orion. It's a giant red star. It's one of those stars that's puffed up so big that if you put it in our solar system, it would be between Jupiter. We don't know when it will blow up. Thousands, tens of thousands of years, probably, but at some point it will. Here's another one, a star called Eta Carina, which is already coming towards the end of its life, and it's kind of burping, right? In a polite way. It's throwing off gases. It's kind of exploding off the surface. The material is forming. There's a star in here, and there are huge bubbles of gas as the star begins to die. And at the very centre, just before it dies, it will have a huge ball of iron. So the iron that's in our blood, and the iron that's in the metal in the chair legs around you, that all came from the centre of a massive star. So you, inside you, contain material that was once upon a time inside the centre of a star. So when someone says to you, astronomy it's not important to me, it's not relevant, well, it is, because you're made of all this material. You're made of all the chemistry. What gets left behind? Well, that depends on how squashed that core becomes at the point at which the star blows up. A normal star, light shines off it, right? If I shone this laser off a star, it would just fly upwards. It wouldn't be bothered by the gravity at all. On a neutron star, gravity is strong enough that it can bend light. Squash the neutron star and make it even denser, the bending is even more extreme. And if you squash it even more, you get to a point where the light falls back down effectively, and you get a black hole. And that's what a black hole is. It's something which is so dense that light can't escape. This is the explosion of a star that was observed in 1054 by the Chinese. We call it the crab. It's supposed to look like a crab. I've never seen a crab that looked quite that messy before. But there's an object, one of these two stars down in here, is the pulsar. It's the neutron star, the crushed nuclear reactor. And all that other stuff, moving at thousands of kilometers per second, is all the chemistry that that star has made being recycled, being thrown back out into the universe. Winds from galaxies can move that material around as well. They can blow what are called super winds, tens of thousands of kilometers per second, blowing out of galaxies, mixing up the chemistry of the galaxy, making it all move around. And then when galaxies collide, beautiful Hubble, this is one spiral galaxy here and another one down here, they basically collide and gravity has ripped them to shreds. But it's mixed up all the material. So as they die, all of those gas clouds collide into each other, get squashed, new stars are born. You get huge amounts of starbirth, these regions of brightness here, where baby stars are being born as the galaxies are dying. There you go. That's why you should care about stars in a sense, because the chemistry of the whole universe, and including you and life, right, these basic four elements for life, all bar hydrogen, are produced inside stars. So if it wasn't for stars, there wouldn't be the chemistry for life. There wouldn't be the chemistry for us and all the other things that we see around us. I shall stop there. Thanks very much.